Yeah, thanks a lot for the introduction. Thanks a lot for having me here. Actually, the last time there was one of these workshops here that I attended, I was living in LA, but it was remote anyway because of COVID. Whereas this time, I actually moved in the meantime back to Germany. And so anyway, now I'm here in person. So yeah, thanks again for having me. And yeah, I moved to Germany end of last year, basically. And in the meantime, I was, I guess, mostly busy with like building a group there and things. So I will present some work together with AWS. And as Lynn already mentioned, Sam and Andras are here, and they probably know more about the topic than I do. So yeah, please feel to discuss with them as well. Good. Yes. So actually, the topic is a very basic one, if you want, and also what we do is kind of conceptually simple. But nevertheless, I like to talk about it from time to time because I think it could be very useful, and I want to like advertise it a bit more broadly. Okay. So quick question: how long should I take, like for the start? 50 minutes. Okay, perfect. Thank you. Good. Okay, so let's just start with the problem that we look at. So we'd like to do state preparation where the amplitudes of the state are distributed according to some function. So here is an example. This is for the real case, but it doesn't really matter. Okay, so you have a function over some interval AB. And then here we take this kind of uniform grid over this interval. Again, it doesn't really matter. The point is just that you want to create this quantum state where the amplitudes here are given. Of course, you have to normalize things such that you actually have a quantum state. But so that's the basic task given, like the function, the interval, the number of grid points, the spacing you want. Write down a quantum circuit that prepares this state. Good, and yeah, people tell me this is an important subroutine, like depending on what function you look at in quantum algorithms. So it doesn't like solve itself like some computational problem necessarily with some quantum speedup or whatever. But that I would say is also an advantage of this problem because you don't have to compete with any like classical algorithms, right? You just want to kind of solve this problem like once and for all as efficiently as possible, and then this is surely useful, and you can use it for your purposes. And I guess here, yeah, you want to kind of use as few gates as possible. Maybe also like you're interested in depth, and you want to use as few qubits as possible. Of course, if you have like 2 to the n grid points, you will always need n qubits, right, to represent the state. But then you want to have as few additional qubits as possible. Good. Any question about this basic setting? Okay, so let's look a little bit in like what approaches there are already out there in the literature. And I think the standard approach is to use an amplitude oracle. Of course, you also have to construct your amplitude oracle. And one of the things about this approach is then that you kind of have to specify in advance how many bits of precision you want to use for your amplitude oracle, right? You want to like put the value of the function at this point x bar in there, but you need to say like how many bits you want to use that. This is something you specify in advance. Good, and then of course, yeah, you have to implement that oracle. Now you can of course do that with any kind of reversible circuit of your choice. And I think leading approaches, yeah, I'm sorry, by the way, that I don't really have references. I have a slide in the very end. You can also ask me. But I think the leading approach here is that you're kind of, okay, depending on how your function looks like, you use a clever piecewise polynomial approximations of the function. And then for these specific polynomials, you can write down relatively efficient reversible classical circuits, which you could then use in the quantum setting. Okay. Alternatively, what people also do, I saw in the literature, is because this can incur quite a lot of overhead cost, is that they just, instead of actually using the structure of the function, they just store the values, so these f values, in a quantum memory structure in the first place. So then you're just not making use that there's some underlying structure function. You just treat it as like general classical data if you want. Of course, that's not a good sign, right? Like the whole hope is that you can avoid doing this. But for small-scale samples, it seems that this can be sometimes beneficial in terms of finite resource costs. Good. So yeah, let's get back to this amplitude oracle type of approach. What are possible downsides? Well, so one thing that is sometimes problematic is that you have to choose this approximation here in the very start, and you don't necessarily know how the error that you might make there from like finite arithmetics propagates through the problem. Okay, so that's one difficulty. Another one is that if you really want to find these kind of good oracle constructions, you might have to do like a lot of like handcrafted work every time. Yes, please, you implement this.
Yeah, just wonder why you call that amplitude oracle, because you are actually encoding the function in a computational basis.
Well, I guess it's just for like the task itself, because you have here this amplitude.
Okay, that's good. Yes. Okay, thanks.
But it's based on, actually, yeah, I think that's what people call it in the literature. But good, yes. And then, yeah, so you will need ancillas. You need quite a lot of ancillas. In fact, the number of ancillas kind of scale with the degree of the polynomial you need here, as we will see later. And one might argue that this is not suited for what some people call early fault-tolerant regime, where you just want to be as qubit aware as possible. Good, yeah. So these are kind of like maybe two of the downsides. There are other approaches. I won't have time to talk about them in terms of technical details, but there's something called Grover-Rudolph. There's adiabatic state preparation, repeat until success. So I would say these first three approaches, they all have kind of similar downsides as just this like plain amplitude oracle model. There's also a matrix product state preparation, where the idea is basically, okay, so you just try to find a matrix product state with some fixed bond dimension that approximates the state you're actually looking for as well as possible. Here, the thing is, it's kind of unclear how things scale, or in other words, there are no kind of like rigorous guarantees on how well this works. So this one falls a bit out of the line, but all other approaches are kind of similar. Questions? Good, yeah. So what are we going to do? Well, we're just going to use some like off-the-shelf tools that I guess many of you guys know by heart. Namely, we're going to use this framework of quantum eigenvalue transformation, or general version called quantum singular value transformation, and just plug that in. And as we will see, as it's often the case with this framework, this will help us to get better asymptotic, but also better finite size costs for the task at hand. Okay, so let me talk just a little bit about this framework from a very superficial viewpoint. So those that know all the technical details, maybe they shouldn't listen too closely, because I'm probably going to be too crude. But people that don't know about it, yeah, this is the idea. Yeah, so this framework to coherently apply functions to the eigenvalues of a Hermitian matrix. And well, okay, so one important ingredient to encode the Hermitian matrix into a quantum circuit is the so-called block encoding. So the idea is that if you take your n-qubit matrix, so this matrix A is size 2 to the n times 2 to the n, you embed it into a larger n plus m qubit system. And then you want to choose it in a way that you have a larger unitary matrix. Whereas if you throw away the additional m qubits here, okay, this is the sandwiching, the cat 0 tensor m, then what you get is back the original matrix A. Of course, in general, if you want to achieve a unitary, you have to be careful with the normalization of your original matrix, and you might also allow for some approximation error. So this would just be like operator norm here. Yes, and then what this QET framework does is it allows you roughly speaking, to transform this block encoding of your original matrix A into a block encoding of the matrix A to the D, properly normalized again. Okay, and so the idea here is that you can do transformations for general functions, and you do this via polynomial approximations, and the even degree case is the simplest. So I think I have a circuit also on the next slide, but the important part about the implementation cost is that it uses very few ancillas, so very small constant number, plus the gate cost is basically proportional to the degree of the polynomial you look at. So the higher degree the polynomial is, the more expensive your circuit becomes. And I think I have a very simple example circuit here. So you see here you have the block encodings of your original matrix. This is the dagger version of it. And then, yeah, so here is an even degree. Here we need 1 ancilla qubits, and then the way your polynomial, or here, I guess in this case, we could even look at a monomial. Looks like it's that you have different angles, theta, and depending on what you put as angles, you get different polynomials. So you actually need, given the polynomial, you need to compute these angles, right? And there have been lots of work on how to do this best in practice, and so on and so forth, but we just want to use these things as a black box input. Okay. Good, so this is the very simple example for this even degree polynomial, but yeah, you can lift this to general functions via polynomial approximation theory, and this scales very well in general. Okay, so you might wanna use this type of framework. It has been used for basically rewriting the whole quantum algorithm landscape, and yeah, we want to use it for doing this coherent state preparation. Good. Any questions? Good. Then let me continue. So what's the main idea? Actually, there's some flexibility also, I think, and how one wants to do this exactly. So the way we choose to do is the following. So we first create a low cost, a block encoding of this diagonal matrix. Of this matrix, yeah, where the amplitude is given by this sine, just again uniformly spaced. And one of the reasons we start with this is because there is a rather cheap circuit that does this. So you can just use this n-controlled Pauli Y rotation to create a state like that. Okay. And okay, so if you want, this is a 1-1-0 block encoding. So you need 1 ancilla qubit. Normalization is 1 already, and you don't make any error, at least if you can implement this perfectly. And then comes the step where we apply this QET framework, right? So now we want to transform these amplitudes here, which are just given by the sine, weighted by the sine, to the ones we are actually into, which is the function f, right? So the QET framework will allow us to do this if we use a polynomial that approximates well, not our function itself, but some slightly transformed one, right? You have to, since we want to go over this interval AB and not just over the interval around 0, we have to shift things a little bit, and then you have to do this kind of arcsine pre-processing. Good. So now you, in principle, you might start with other low-cost type of block encodings, and I think in the meantime people also did that in the literature, but that's one way of doing things. And then in the last step, okay, you have to run this on the all plus input. So if you look at this picture here, right here is your computational base input. So you would run it on the all plus input, and then you can use a couple of rounds of amplitude amplification, such that if you measure the ancilla qubits, so here we have, you're going to need 3 ancilla qubits, that if you measure and you get 0, all zero state as a result, you actually prepared the state you were looking for, at least like an approximation thereof, because you used the polynomial approximation. Right? And actually, we can use an exact version of amplitude amplification if you use a fourth additional ancilla qubit, and then you can achieve this. You can create this state with probability 1, at least, if you're not making errors. Yes, please.
Yeah. So in your first step, can I ask, like, what's the advantage of using the sine function? Can you use that?
Well, yeah, so in general, you could use other functions that you start from, like you just need to start from some block encoding. I think in practice, it depends on the function f you're interested in, right? Like so the question is, when is the polynomial here of lowest degree of this resulting thing, where you replace this with other functions, potentially. But this is just very cheap to start with, but we haven't like optimized on that front. Or maybe Andrew or Sam, I don't know if you have any further comments. Is that okay? Further question? Yeah, let me go from front to the back.
Well, y is negative 2 to the 0.
Sorry?
The last y rotation is negative to the y is negative.
I am not sure, actually.
And,
Well, there's a minus here. I'm not sure if the signs are correct here.
and another thing is you can also use zero rotation like this. You can use zero rotation, which is, I think it's more intuitive because it's just like diagonal matrix, tensor diagonal matrices.
Yes, yeah, I mean, you can use others, yeah. Andras, yes?
Yeah, for that sign, it's just, okay, this is computer science. If you represent a signed integer, then usually the most significant bit is in minus sign, and that's how you represent negative numbers. So,
Okay, so the accent is actually the sign.
this is a signed integer or signed fixed point binary number. And if you interpret that way, then this is the correct.
Yeah, accent. So accent is actually the sign bit. Right?
Yes, thanks, Andras, thanks, yeah. Yeah, second row there, yeah.
Yeah, the last step, using that amplitude amplification, does that mean this whole procedure will be exponentially long?
No, it will just be done a couple of times.
But in general, amplitude amplification provides square root speed up.
Yes.
And therefore, to achieve a maximum close to 1 amplitude, that takes exponentially long.
So the gate complexity of this will be proportional to n. So it's going to be linear n. So it's not going to be exponential.
So it's just the last step.
Yes.
Yeah, so in general,
Yes.
get that amplitude close to 1 high.
Yes.
That takes wholly 2 to the power of n times.
But we will only have to run this, like, I think, twice or something in practice.
This is the last step. Yeah,
Yes.
because when you get to that state,
Yes.
you're not guaranteed to be in that 0, 0, 0 state, right?
Well, okay, let me show here this, maybe. Yeah, we can get to the next question in a second. Yeah, so this is the sign block encoding. This is then you take this sign block encoding, so this whole box is just this box, right? And then this is your whole circuit. And then the last one, well, this is this exact form of amplitude amplification, where this whole box is now the UF in here. Okay, so now the question is how many times you have to run this whole thing, but it's not going to be exponentially many times. Or I mean, it depends, yeah, depends. But, thank you. Yes, please, sorry.
So back to the previous slides, for the first rotation gate, it is actually the angle is very small, and I also wonder in practice, is it easy to implement this? Like this is exponential small rotation gate.
Sorry, what's the question?
For the first gate,
yes, please.
Control rotation y. This is 2 to 1 minus n, right? And when it's large and this is exponentially small. I was wondering maybe from a practical perspective, and it is easy to implement.
If this is actually easy to, it depends how you want to like compile it down. Yes, you mean like because if n is, I don't know, some number like 20 or something, then you have to like resolve these angles with sufficient precision, kind of. Is that the question? Or yes, so we're not thinking about noisy gates and stuff. So this I don't know. Yeah. I think Marius was next.
Yeah, if you go back to your next, I mean the slide you want to talk about.
Yes.
So does it always happen that this UF and UF dagger appear in pairs?
I thought so.
I
Is
heard,
that important?
this
Or?
is just because I heard from experimental talks that for some reason this is more stable. And myself find that mysterious, but I find it very curious.
So this I have no clue about. But you can run any amplitude amplification scheme of your choice here.
This UF dagger, it seems to be stabilizing things for some weird reason, which I don't understand, but find completely interesting.
Yeah, that's just on compute.
Yeah, I know.
Yeah, that makes it. Yeah. So I understand. Because your amplitude amplification is based on just 3 qubits. So at most that's 8 steps. So thank you. I understand.
Okay, yeah.
Yeah.
Good. Where else we have? Yeah, sorry.
I had a small question. So I'm used to noisy quantum computing, so I'm not familiar. But how do you construct a RY gate with a small angle from Clifford plus T? Because like T is pi over 8, so like if it's 20, how do you get to the...
Yes, so we are not making any like original contribution on that front. We would just use stuff that is available in literature. So, I mean, I'm just going to count basically all these gates. And then there are ways of counting, well, some standard ways of counting, like how many Clifford, non-Clifford gates this amounts to. But if one wants to run this in practice, indeed, one has to think about all these questions, right? Yeah. Yes.
So is U sine a permission blocking coding or just a blocking coding?
So what's the difference here? I would just use here this one, but with alpha 1 and epsilon 0.
So yeah, what I mean is, if it's a permission blocking coding, you don't need U sine dagger.
I see. Okay.
Yeah, and one more thing is,
Yes, okay.
if you have the sine bit, you actually need one more bit to get 1 over 2 to the n like resolution.
Yes, that's true. Yeah, okay. So these are more like placeholder pictures, but yes, yeah. Understood. Thank you. I think maybe we should move on and then we can have some more questions in the end. I don't have too many slides. I'm happy to have lots of questions. But maybe just for the storyline to continue. Yes, okay. So this is the overall rough idea. This is our overall the rough circuits. And of course now to quantify how well this scales, I wouldn't say in practice in terms of like noisy implementation stuff, but just like, you know, what's the asymptotic scaling kind of. The crucial point is, of course, is going to be, well, first of all, what degree of polynomial do you need here? And second of all, how does the error of the approximation here scale or propagate to your final state, right? This you have to analyze. Okay, and so yeah, let me get through that step by step. So an important quantity that appears in all these other approaches on quantum state preparation is this filling fraction or L2 norm filling fraction. So usually I try to draw a picture, which I should probably put on my slide. But okay, so if you have some type of function, right, I don't know, something like this, and then you're interested in this interval a, b. So then here you have b minus a, right? And then maybe here you have the f max. So the idea is, and then you would have a grid here though, right? Something like that. So you kind of want to look at, in this L2 norm, how much of this overall area here, right, kind of, is filled by the function. So this is kind of the L2 area of the function, this is the overall area. And then if n is large, remember like n scales like 2 to the small n, right? And so because we'll have to compute this quantity, you might want to approximate it with this continuous version thereof. And then, okay, you also have to say like how well this approximation works. Good. So the first theorem, which is the more complicated one, is that, okay, so you now want a polynomial approximation, f tilde, of your original function f, that has a certain degree, then you can prepare a state for this polynomial, that is the function f tilde, that is in trace distance close to the actual state that you want to prepare. And the scaling is as follows. Well, you need 4 ancilla qubits, only this constant small number, plus the number of gates you need scaled with n. This is the number of qubits you have. It scales with the degree of the polynomial and this filling fraction, now of the approximation f tilde. But of course, the question is now how this degree scales with respect to this epsilon that you want to get to. And the delta scales with epsilon, and again, a factor of this filling fraction. And okay, there's this star here. So more technically, you have this pre-processing, this arc sine thing. You have to also normalize things to fit in the framework. And well, for this worst case guarantees to work, you need an L infinity approximation. Okay, so this is the general statement. Of course, now the scaling of this, it all depends on this d delta. And so the question is now, can we make some statements about this d delta? And then the simplified version of the theorem is like if you have a nice function, there's again a star here. So the star means that your approximation is basically exponentially good in the degree of the polynomial. Then you can create this state that is epsilon close to the state you want, and things scale like that. So there's this tilde which hides some things, but the main complexities are scaling with n, log 1 over epsilon, and this filling fraction, plus only these 4 ancilla cubes. So I think this is a very nice scaling, and it's not only that this works well in terms of this analytics, because there might be a lot of like smaller factors hidden in this notation. I would claim that if you do these things like in practice, then this hidden factor is basically smaller than 1. Okay, so it also behaves very well in practice. Yes, you have a question.
So can you make a comment about what you mean by sufficiently smooth? Is it smooth or smooth up, like up to some in it?
Well, okay, so actually maybe you just want to say this. So sufficiently smooth means this. But maybe Andras can comment more, and he worked a lot on these things. But yeah, that's kind of. But again, like in practice, you will have this scaling. Like you give, unless your function is very non-smooth with a lot of like jumping. But then you can do other tricks, which we will see a bit later if we still have time.
So if your function is ck, that does your result hold?
ck means k-fold.
K times continuous to differential.
I mean, the k might come in some form, but yes, roughly yes. Yes, Anthony.
Funny question, but like I know many functions you care about in life are really smooth and nice, but what would be an example that it's not smooth and nice? Like this jumping function, like what?
Where you have this like triangle function and stuff like that, or?
And in that case, it's like how does it break, or like we just kind of just manually smooth out the edges and then it still be fine.
Yeah, you can pull tricks like that. Yeah, so either you can do it piecewise again, everything. Or you can, for example, if you have like a jumping point like that, you can kind of open up the function a bit and then, yeah, look for like a continuous interpolation. And this will drive up the cost a little, but I think, yeah, the rough scaling should stay like that as well. Yeah, so that's what I'm saying, like in practice, this is not necessarily a bottleneck. Yeah.
I'm a little surprised about the number 4. It seems as if independently of the smoothness, independently.
Exactly. That's the whole strength of the approach. Yes.
But, if you smooth it around the corner like that, you won't get exponential scaling. It usually only works for analytical functions.
Well, but look. So if you
if it's randomly a step function and you smooth it around the corner.
I mean, if you do this, right?
Yeah.
Like you can either just do whatever this whole thing I presented here and then do the same here. That's piecewise, right? Or you could like open this up here. So you could take this and look instead of I mean, you have to do these things coherently, but you could like open it up like this kind of. And now you're just looking for some function over the whole interval that from here to here and from here to here, right? It's the same as here, but you don't care what happens in between here, kind of.
Yeah, but still you won't get the exponential scaling on like the whole interval. I don't think
Well, if you do something like that and you just work with that function, that one is perfectly smooth again, right? So then the question is just, what are the costs of opening it up like this coherently and then closing it again, no?
I think the comment is correct, that if you literally want to get this scaling, you need complex analyticity, which is hard to construct there. You can get a Gavry type of smoothness, which is slightly weaker than exponential scaling, but still super.
Okay, yes. Okay.
But you can use, instead of the sine function, you can use some function which already.
And you can use the pre-processing to work with this. Yeah. I mean, the pre-processing, the block encoding to start with, yes.
Just a comment here that okay, if you have a fixed function, even if you open up, you probably have this scaling issue. But now, because we don't care about what happens in the opening up, like as you go more and more precise, you always change the function where you don't care about. And that way you can actually have this scaling. But for different levels of approximation, you maybe have different phantom functions. That way it works.
Good. So thanks a lot for the discussion. So that's kind of the analytical worst case guarantee. Now in practice, of course, you might do all kinds of things you like to find your best polynomial. And so in particular, like intuitively in the end, you only need your approximation to be good on this kind of discrete grid, right? So I might even do some L2 approximation things, whatever works well in practice. So I think it's very nice that you can prove, like, in terms of asymptotic complexities, this scales very well. But then as a separate question, it's kind of like, okay, so how do you do this in the finite size regime? You have a lot of freedom, and it actually also works quite nicely, I think, yeah.
I wonder why you need exactly 4 ancilla qubits.
Okay, so I think 1 is to do the sine block encoding. Then 2 is for the QET. And 1 is for the exact form of amplitude amplification. And if you have more assumptions on your function, you might have fewer. So, okay. Yes, Robin.
Do you have like a motivating example of like a smooth function? Presumably there was a smooth function that you wanted to create the state for, and that's why you started this project. Like, what's a good function to keep in mind?
Gaussian, I think. Yeah, let's do this slide first then. Yeah. Yeah, you look at the Gaussian. Okay, there are some assumptions here, but this gives you the rough scaling. I think Andras, you said you might be able to improve this, but this is current scaling. So yeah, you see, if you now work out these polynomial approximations, you work out this L2 filling fraction things, this is the scaling you get. And I think this is basically the best you can hope for, right? N and log 1 over epsilon. So I think that's very nice. And 3 ancilla qubits, not hundreds of ancilla qubits, as all other approaches. You can also do this here for this Kaiser window state, which is important for phase estimation, I think, also in your work here. Anyway, that's a very good example, I think. Good, but okay, so.
Sorry, how does the cost depend on beta?
Okay, so here, to get this nice form, the beta is just larger or equal than log 1 over epsilon. So the general function, I don't remember. Do you guys remember? It's like beta to the 4 or something. I can.
So it's even better. If beta is smaller than log 1 over epsilon, then you get even more savings. So this is always an upper bound.
Yes, but I don't remember the exact, but it's in our paper. Maybe you, sorry, yeah.
Oh, I see. Now I know what the question was. Because this one is because you're trying to prepare f beta equals exponential without further normalization, right? If you were to prepare a Gaussian distribution or square root of the Gaussian distribution, I think then you're going to see that the potential drawback of the approach, because the f infinity norm will depend on beta, right? So let's say if you were to propose prepare the distribution, there is a scaling factor in front, square root of beta, right? And if there is a method that directly prepares the probability distribution, that could be better than this method.
Well, then the Gaussian is exponentially quickly decaying, so you can always just prepare the state where it matters and say amplitudes are 0 everywhere else. up to absolute precision, you're right. So your window is never going to be bigger than, I don't know, whatever.
1 over
1 over
base.
epsilon. Log 1 over epsilon or something. It's never going to be bigger.
I'm not sure we're talking about the same thing. So if we were to prepare a square root of a normalized Gaussian distribution, then the f infinity is going to be.
Yeah,
you
but
need to scale it down.
so all these you can just focus on the window which has with roughly your standard deviation.
Okay.
And on the standard deviation wide window, your function is up to constants multiplicatively the same. So there is no issue with Philip fraction. Okay, maybe it's very high, but it's roughly uniform.
I mean, okay, this is just the example. I agree that if you look at specific functions, you might have to pull lots of tricks, but I think there should not be any.
So anyway, for that beta constraint shouldn't be even there. It can be, you can just remove it completely, it's fine.
Okay. Yes?
Do you mean that the Kaiser window function can be represented with Gaussian? Because it's on this slide, the size title is Gaussian.
Well, I just wanted to mention, I didn't mean to imply that necessarily, but I just wanted to, okay, the way we do this, it also works for this function, and people have been interested in this function, and we haven't found any, because there are other methods that people prepare Gaussians, but we haven't found any other methods where they've specifically looked at how to prepare this.
Does it have anything to do with this one, like the Kaiser window function?
I guess not the way it's stated now, no. Good, okay. Yes, I'm happy to discuss concrete examples during the week also. So here is a quick table. Sorry, let me just guide you through it. So this is our work here. This is the scaling you saw, basically, ancilla qubit, rigorous bounds. We need these polynomial approximations. It also works in a Fourier type of picture. So these are some of the other approaches I mentioned. Yeah, the gate scaling is somewhat similar, but you see the difference is the number of ancillas scales, well, it scales with the number of bits of precision you want, of course, but it also scales with another polynomial degree, which comes from these piecewise polynomial approximations that you use to constructing the amplitude and oracles. So this is really the main take-home message here, that it scales much better in terms of ancillas, which, again, in this early fault-tolerant regime might be of big concern. There's the matrix product state, which is kind of different, but I don't want to discuss more, I think. Good, so that's this quick table. Then we already saw this Gaussian. So the Kaiser window state, or I mentioned them. I think Sam also ran this numerical benchmarking for this tanh function, just to see kind of the finite size numbers, right? Because on the last slide, we had these analytical dependencies. Good, yeah, so if you look at the interval 0, 1, choose n equals 32, so you have a spacing of 2 to the 32, right? Then, okay, you can see again, we need like 2 orders of magnitude fewer ancillas, whereas the gate count is kind of comparable. Of course, you might question these numbers, these exact numbers, but if you want, like for our methods, this is kind of an upper bound, right? Like this is something one can do, whereas for the other methods, we try to use kind of the state-of-the-art amplitude oracles, and then I think we even neglected all the other gate costs. It was just the cost of preparing this amplitude oracle. Good. Yes, so now let me actually check the time. So I think I have a few more slides on how to run the algorithm, but I might actually skip those because we had lots of discussions on this already. This is the circuit again. Just emphasizing that a lot of stuff goes into the pre-processing, right? So you have to find this polynomial approximation. You have to compute this L2 norm filling fraction or its continuous version thereof. So if n, this is too large, you can work with this. And this approximation is going to be provably good under some assumptions. So these complexities you saw, they took into account that you have to be able to compute these things efficiently, classically as well. So there's no like exponential things hidden here. You have to compute the QET angles. Good. Then quickly, the extensions. I think I already mentioned these two examples, right? So here is this example, this triangle function that I already drew here. So there are ways of dealing with non-continuities. But I mean, okay, this is like a general method. So if you have your concrete function at hand, you might want to optimize all of these ingredients, right? And then look at the resulting cost. Yeah, I also already mentioned there's like a Fourier-based version of QET, which we can also do things for. I think, yeah, there's this one example. So if your function is very like much given in terms of the Fourier series in the first place, and you might not have a closed form expression otherwise, this Fourier version might perform better in practice. Yeah, I think there's a numerical example here as well, but okay, this is just a number. Good. So outlook, well, first, I guess, quick conclusion. So I presented these methods for preparing quantum states whose amplitudes are given by some known function. It's based on the quantum eigenvalue transformation. The main selling point is that it works well analytically, it works well numerically, also in practice, and it has orders of magnitude savings in the number of ancilla qubits you need. And I would hope that this is really the way you want to do this task going forward. And so for that, of course, we would need to do many, many more things. I think at AWS, they're also working on follow-up versions of this. Sophia is also here, exactly. Yeah, one needs to like benchmark this, have like the proper tools to actually implement this in practice and so on and so forth. There are some examples where this might be hard and one needs to think more about things. Yeah, the multivariate version is also interesting. But I think I want to conclude here, and we can have discussions later on. Let me just say that I am still hiring, also in London. People are interested to go to Imperial College. Yeah, thanks for your attention.